Hi everyone, welcome. It's good to see you again. Second derivative test. Practice problems. Ooh, whoa, there's some really great stuff in these notes today. All right, so let's start with some bell work. Bell work for assignment 62. Okay, given d dx f of x equals 2g of x, and h of x equals x squared. Find the derivative of f of h of x. Okay, so what's that going to look like? F eats h. So there's an f of x. There's an h of x. Pause the video, give it a try, come back when you're done. Well, yes, so I want to take the derivative of f of h of x, which means I need to plug this in there. So now I'm looking at the derivative with respect to x of f of x squared equals 2 times g of, I replaced x with x squared. Okay, so we know the derivative of f is this thing. I don't think I like that. Let's try it again. Okay, I want f of h of x is my y, and my y prime is going to be the derivative of the outside, leave the inside alone, times the derivative of the inside. Now, what can we say about these things? Well, the derivative of f, this is the derivative of f, is 2g of x. So I can replace this with 2g of, well, wait a second. I had no x, no h of x. Okay. Times h prime of x. Okay. So I did have to take this and plug it in there. Oh, and I still do though, because h of x here is that. So I've got x squared. And what about h prime of x? Well, the derivative of this is 2x. So I end up with 4x g of x squared. Huh. Nice. Do you need me to go through it again? All right, let's go through it again. So we've got some knowledge that the derivative of f is 2 times g. And we know that h is x squared. So if we want to find f of h's derivative, we take the derivative of the outside, we leave the inside alone, and then we multiply by the derivative of the inside. Now, I want everything in terms of x, so I need f prime of h. I need f prime of x squared. Well, remember what f prime was. The derivative of f is 2g. So that's 2g of h. Times, we need the derivative of h. Well, there's h. The derivative of h is 2x. All right. Yeah, we can't be thrown off by notation. No, definitely not. All right, so will you find y squared over 2 plus 3y equals x squared over 2 minus 2x plus 22. Okay. And so the question I want to ask is, do I have a min or max x equals 2? Huh. Well, that's an interesting question. Okay, so what do I have to do in order to determine if I have a min or a max? Well, I want to make an f prime sign chart, and I want to check endpoints if there are any, or find out where f prime is equal to 0 or f prime is undefined, and test on either side of those points. Okay, so let's take a derivative. Derivative here, y times dy dx, right? Because you're taking the derivative of the outside squaring, which brings that down, and then those cancel, and you're leaving the inside alone. And then you're coming back and multiplying by the derivative of the inside with respect to x. The derivative here, 3 dy dx. The derivative here, x minus 2. So dy dx times y plus 3, x minus 2, and I get dy dx equals x minus 2 over y plus 3. Well, nice. Okay, so now I have a derivative. And I know that if I evaluate at x equals 2, 2 minus 2 is 0. So I have a 0 slope. Well, that's great. But now what? How do I check the other sides? Like, because my derivative has not just x's, but y's in it as well. And so now I feel like, okay, I got this point here, but I got y values that could be here or here, and y values that could be here or here, as well as the x values on either side. So this becomes really, really, really hard to find that plus to minus or that minus to plus that I sort of depend on with the first derivative test. Instead, I need the second derivative test. Second derivative test. Sure. So remember the second derivative test says if f prime of a equals 0 and f double prime of a is less than 0, that's this picture, concave down, horizontal tangent, there's x equals a, then we have an x. Versus f prime of a equals 0, but now f double prime of a is greater than 0. That's this situation. And that gives us a min. So we need to figure out f double prime and plug in this point and see what happens. So here's f. Let's find f double prime. X minus 2, x plus y plus 3. So low d high minus high d low over low squared. Nice. Remember though, we want to replace this dy dx with this stuff. X minus 2, y plus 3. Okay. Now, I want to know what the value of this is when x equals 2. However, there are also some y values. I've got to plug something in for y. No. How am I supposed to do that? Okay, so hold on to this thought for a moment, and let's go back to Algebra 2. So x equals 2, and I want to know the y value. I'm going to take these and replace them with 2. And then I'll have an equation that only has y's, and I'll solve that equation. So I'm going to have y squared over 2 plus 3y equals 2 squared is 4, 4 divided by 2 is 2, 2 times 2 is 4, plus 22. 24 minus 4 is 20. I don't like having that fraction, so I'm going to multiply everywhere by 2. Y squared plus 6y equals 40. And then I'm going to move that over. I have y squared plus 6y minus 40 equals 0. So y plus 10, y minus 4. I know that y equals negative 10, and positive 4. So actually, I have two different things going on here, don't I? All right, so at x equals 2 and y equals negative 10, and I have x equals 2 and y equals 4. Now I'm going to take these values, these ordered pairs, and one at a time I'm going to plug them in here. Remember, this is our second derivative test. If the second derivative is greater than 0, then we know we have concave up, and so we have a min. If this second derivative is less than 0, we know concave down, horizontal asymptote, we know we have a max. So we want to find out when we plug in this ordered pair, do I get a positive number or a negative number? I really don't care what the number is. I just want to know if it's positive or negative. So negative 10 plus 3 is negative 7, times 1 is negative 7. And then here, 2 minus 2 is 0. Well, all that goes away. And on the bottom, negative 10 plus 3 is negative 7. Negative 7 squared is 49. This is less than 0, which means concave down. Since f double prime is negative, we know that we have a max here. Now, what if we plug in this? Well, these are still going to create zeros, so I don't have to worry about that. If I plug in a 4, I have 7 on top. I have positive 49 on the bottom. I have positive over positive is positive. Second derivative positive means the function is concave up, and so I have a min here. Justification sentence. There is a max at 2, negative 10 because y prime, no, I don't want to do that. I want to say, why do I want to say? I want to say because dy dx at 2, negative 10 equals 0, and the second derivative is less than 0. There's my second derivative test, or the second derivative test for maxes and mins justification sentence. Well, that was cool. Yeah, and doable, as opposed to doing it the other way. Felt very not happy. So I just want to do some practice now of stuff we've been talking about recently. Wow. Yeah. First, a little review of MVT. Was that nice of me to tell you it was an MVT problem? Y equals e to the x squared minus 4x on 0 to 4. Okay, so first, do the preconditions for MVT apply here? Oh, you don't remember the preconditions? Shame. So the preconditions were if f is continuous on an interval and differentiable on the open interval, then, okay, so is this function continuous? Sure, this is exponential growth continuous. This is a parabola that points up. I'm multiplying them together. Both of these have a domain of negative infinity to infinity, so I definitely don't have to worry about that little piece. So definitely continuous. What about differentiable? Well, the function is first continuous on that interval. Great. And can you take a derivative here? Does the derivative exist everywhere here? Sure. We know that derivative e to the x squared minus 4x plus e to the x 2x minus 4. Or e to the x times x squared minus 2x minus 4. So here's our f prime. Look, this exists everywhere. That exists everywhere. So f prime exists everywhere. Certainly on that interval. All right. So we've met the preconditions. Great. But what does that mean? Like, okay, so Yes, uh, this function is continuous on the closed interval and differentiable on the open interval, then there must be at least one point. We're going to call that one point x equals c, such that f prime at c equals f of b minus f of a over b minus a. And when we talked about this in the earlier video, we said that this is instantaneous rate of change and this was average rate of change. This is the slope at x equals c. This is the slope of the secant connecting x equals a and x equals b on the f of x graph. So we're wondering when the instantaneous rate of change equals the average rate of change. And MDT says it's going to happen at least once for any function that meets these two prerequisites. Okay, so I need the derivative and I need the average rate of change. Since I've already erased the derivative and have to do it again, let's find the average rate of change while we're here. So these are going to be 4s, and these are going to be 0s. F of 4, that's 0, right? Because 0 times e to the 4th is 0. Okay, so 0. F of 0 is 0. It looks like my slope is 0. Okay, so what I know is that there's at least one point called x equals c, where the average rate of change is equal to the instantaneous rate of change is equal to 0. Okay? So what's going to happen here? I need to set the derivative equal to that slope number. So what was that derivative again? It was e to the x squared minus 4x plus e to the x 2x minus 4, or e to the x squared minus 2x minus 4. There's y prime. And we want to know when the instantaneous rate of change is equal to 0 minus 0, 4, or 0. So I want to set this equal to 0. Well, e to the x, it's never equal to 0. So I only have to worry about this. Sadly, this is not factorable. And because this is not factorable, I'm going to have to use quadratic formula. So x equals negative b plus a minus square root b squared minus 4a c 1 over 2a. So I've got 2 plus a minus 2 root 5 over 2. Dink, dink, dink. So 1 plus a minus root 5. At these places, the tangent line will have the same slope as the average rate of change on this function on that interval. Nice. Turns out there were 2. All right. Hey, since we went through this problem and did it as an MDT problem, why don't we do maxes and mins now? Right? We've already found y equals e to the x, y prime equals e to the x squared minus 2x minus 4. So here's our y prime, and I'd like to know when y has a max or a min. So I got my y prime, set my y prime equal to 0. This is never equal to 0. We already found when this was equal to 0, that was going to be plus or minus 1 plus root 5. So I've got 1 minus root 5 and 1 plus root 5. It's a y prime sign chart. Test 1, test 5, test negative 5. Okay. This is always positive. Whether I plug in a positive number or a negative number, this is always positive. This is always above the x-axis. Remember the horizontal asymptote of that y equals 0? Okay, so positive times negative 5 times negative 5 is 25. minus 2 times minus 5 is positive 10, so now I've got 35, and that's a plus. I plug in a 1. This is positive. 1 minus 2 is negative 1, minus 4 is negative 5. Negative 5 times a positive is a negative. And if I plug in a 5, I have 25 minus 10 is 15, minus 4 is 11, and that's also positive. So what do you see? Well, I see that there's a max here, and because I go from negative to positive on y prime, I see a min here. Okay, so max at 1 minus root 5, min at 1 plus root 5. Fabulous. But wait a moment. Yeah. Sorry, you forgot to pay attention to the restriction. 1 minus root 5 is a negative number. And I know that because this is bigger than the square root of 4. Square root of 4 is 2. 1 minus 2, sorry, that's negative. I have to stop here at 0. This is a little bigger than 2, but it's smaller than 3. And 3 plus 1 would be 4. So it's to the left of the same point over here. 4. All right, so things have changed. I mean, this minus is still good. This plus is still good because we were checking on either side of this. But now I have endpoints. And so while I want to say that there's a min here, think about what's happening. Y prime is negative from this point. From this point, that means y is decreasing. So this is a max. And what about here? Well, y prime is positive, so y must be increasing until I get to x equals 4. And so that's also a max. And how did section 5.1 say that we could figure out which of these was the absolute max? We would have to take this and plug it in here, and we would have to take this and plug it in here. We might get this one bigger than that. We might get this one bigger than that. We might get there the same. So what happens? 0 times 1, that's 0. So max at 0, 0. And if I plug in 4, that's 0 times e to the 4th. So 4, 0. So the value of the max is 0 in both cases. I don't know what the value of the min is, because frankly, I don't want to plug that in there. But luckily, we're almost never asked, what is the min? What is the max? We're often asked, where is the min? Where is the max? But when we are asked, what is the max? We have to take that place where the max occurs and plug it into that original function to find the y value there. All right, so what do we know? We know that we have a max, a min. We can write those justification sentences. We know because y prime is negative that y must be decreasing from 0 to 1 plus root 5. And because y prime is positive, y must be increasing from 1 plus root 5 to 4. All right, now it's time for us to consider concavity. Y double prime, e to the x, 2x minus 2, plus e to the x squared minus 2x minus 1. Factor out that e to the x, get x squared, these cancel, and 6. 1 double prime. This is never equal to 0. This is equal to 0 at plus and minus root 6. However, remember we're still on this bounded interval. So can I have negative root 6? No negative numbers. So I've only got root 6 here. Remember, this is the square root of 16, so it's got to be on this side of that. So let's test stuff on either side, like 1 and 3. 9 minus 6, positive times positive. 0, what did I put here? Oh, 1. 1 minus 6 is negative 5 times e to the 1. So positive times negative, I get a negative. Look, I've got a sign change on y double prime. That means this is the location of an inflection point on this graph. I also know that this graph is concave down from 0 to root 6, and this graph is concave up from root 6 to 4. All right. Yeah, you really do need all of that stuff. And you need to be able to write the justification sentences. And you need to be able to do it by hand, but you also need to be able to do it on the calculator. So how about this one? Because I really don't want to take the derivative of this by hand. E to the minus 0.3x. Here's our dear friend logistic function. Why don't you find maxes and mins, increasing, decreasing, inflection point, concave up, concave down. Use your calculator. This is a with calculator problem. Stop wasting time doing this by hand the long way, when really, this is on the calculator portion of the test. You need to use your calculator here. Okay. Come back when you're done. Welcome back. So I'm cheating. I know what this graph looks like. See? It's got y equals 0, and y equals 1500 as our asymptotes. That's always my upper asymptote. This is always my lower asymptote. Now, what do we know about this function? Well, 1, I don't see any mins and maxes. 2, this function is always increasing. 3, there's an inflection point here. And 4, I see concave up and then concave down. And the reason I point this stuff out is because often on tests, when I give something like this, students just don't spend any time thinking about the stuff they know about it. They just pull out the calculator and start typing stuff in. Okay, so my function here is 1500 divided by 1 plus 200 e to the negative 0.3x. And all that stuff in the denominator has to be in parentheses. Okay, good. And so I know the top is 1500, so I want to change y max to 1500. This can be 0. And I don't know if I'm going to get there 0 to 10, but 200 seems pretty good. So let's see what happens. I don't see any. Oh, look, there is little guy down there. Wow, that means I need a lot more X stuff. Or, what am I trying to grab? Stop. Oh, this is still taking. Okay, so here's my function, and it looked like I needed a whole lot more y stuff, x stuff going on. So let's go up to 100, steps at 10, and see what happens. There we go. There's my function. Yeah, I don't see any mins or maxes there, but that's okay. I don't have to see them. I should be able to go to y equals and say, hey, mderiv, will you take the derivative of y1 and show me what it looks like? Well, let's change that here and we go again. I still want 0 to 100, but my y values, these are the slope numbers of the original graph. Oh, look at that. Positive, negative. Oh, it doesn't go negative, does it? It comes very close to 0. Let's change the given. Let's bring it close and see if it works. Okay, so changing my y values and going -1. And we're looking for any places where we might cross the x-axis. But we already know. We're not gonna do that. Remember, this is y prime. This over here is y. So don't be surprised that this thing is going downhill and this thing is going uphill. Okay? Now, in fact, what I do want to say though is, let's go back to negative And let's change this to 100. Wow, the slope is bigger than 100. Seems like it is. Let's follow these points. Okay, so that's COVID curve. You see it? COVID curve about flattening the curve. This curve is the derivative of this logistic function. This is number of people infected. The slopes are people infected per day. The infection rate spreads really fast until we get to this point where people are still being infected but at a lower rate. That point there is a 0 on the second derivative, which is the inflection point on the original graph. So if we find this maximum, we know the x value of this point. Be careful. Some students say they find this maximum and they write this maximum ordered pair here. No. Remember, these are x values, but these are y prime values, not y values. Okay, so what do I see here? Well, I see y prime is always positive, which means y must be always increasing. Y increasing on negative infinity to infinity. Y decreasing never. No mins or maxes, because we have no sign change in y prime. Now, what about concavity? Well, we could do that one of two ways. We could come back over here and we could graph that second derivative and fiddle around with a window to find it. Graph. Oh, I need to get more y there. We know we need more y. Whoa, that's so tiny. Definitely going to change the y values. Okay. By the way, second derivative takes a long time to graph. So I want more y. So I'm going to do negative 10 to 10 and step 7. So this is y double prime now. Y double prime is above the x-axis, so y must be concave up. Then y double prime is below the x-axis, so y must be concave down. At this point, where we change from y double prime positive to y double prime negative, this point is our inflection point. So if we do second, calculate, second, calculate, mashing the wrong buttons. Second, calculate 0. And our 0 is over here, not here. Did I get positive yet? Still negative. There we go. Enter, enter, enter. So, what do we see here? We see, it's still thinking. So much work. I mean, just be patient, because think about you and how long it would take you to A, find the second derivative by hand, and then B, set that second derivative equal to 0 and solve. And so I'm kind of excited that my calculator can do that in less than a minute, because I know it would take me more than a minute. It looks like x is 17 point, oh, I really do wish I had eyes that worked. 17.661. Great. Now, let's go back to this picture. Here. This was our curve. We just found that this x value was 17.661. That y value of 0, no, is not the y value here. The y value here is when we take this number and we plug it into this function. But wait, remember what we said in August? We said that this inflection point always occurs at L divided by 2. So that's where that is. So now, let's talk not about increasing, decreasing, and maxes and mins. Let's say I have an inflection point at x equals 17.661 because y double prime changes sign there. And what else do I know? Well, I know that on my y double prime graph, we had positive values here and negative values here. And because of that, I know that y is concave up on, well, sometimes we start at 0 and sometimes we start at negative infinity. And I wasn't clear at the beginning, so I'm going to go with negative infinity to 17.661 because y double prime is greater than 0 on that interval. And I guess I should write that out because y double prime is greater than 0 on negative infinity to 17.661. And y is concave down on 17.661 to positive infinity because y double prime is less than 0 on 17.661, infinity. All right, so please make sure you're comfortable doing this stuff by hand and with a calculator. I might recommend, if you were looking for some more problems to practice with, x squared sine x, y equals e to the x over x squared minus 9, and y equals e to the x plus sine x. So these things are all going to just, you don't want to go anywhere near them with algebra-based stuff, just on the calculator. And you should practice that because half of our exam is with calculator. So be ready for that. If you were looking for some more practice by hand, maybe without calculator, y equals x squared square root 3 minus x, or even y equals e to the x squared minus 3. Okay? Give those a try. If you're feeling like you need more practice, feel free to reach out to me and let me know if you want to check them or you need help with them. All right. Take care, everyone.